Google manages over 30 billion gigabytes of data, more than 100,000 searches every second all over the world without ever going down. And in 2003, this is what that all looked like. This refrigerator-looking thing, along with 1,000 copies of it, managed almost the entire internet to the entire human race. And it all ran on a bunch of systems that you can download online practically for free and use less power per consumption than a laptop. So does this mean you could have made your own Google back in the 2000s? Well, yes. This all started as a research project for two guys at Stanford. But also, no, because you have to understand how this all works. Before we continue, let's talk about Rolladell.com. This is not another freelance marketplace. Rolladell was built for freelancers who value freedom, privacy, and control. This is where individuals and businesses of all sizes post their service and get hired in a flexible manner. Design, programming, copywriting, SEO, social media, marketing, and much more. There's a professional client waiting to pay for your service. After you've signed up, create proposal, describing your project by telling clients about your proposal. Boom. Receive messages from interested clients and work with them. Guess what? You can become a buyer and purchase services with your local payment options. You're in control. Visit Rolladell.com to get started now. So let's start with data. Managing data is usually pretty simple, like big server, big computer, and MySQL. You can think of MySQL simply like a giant, complicated spreadsheet, and that's exactly what Google was using. So in the early days, Google was just a giant spreadsheet, and it worked up until that spreadsheet started growing to billions of rows by billions of columns and expanding every single day. That's when Google realized this system was not going to stand up and saw query response times. How fast Google could pull out specific information. Slow down with the stability of the system coming into question. The issue here with the MySQL setup Google had was scaling in traditional databases. Scaling usually meant adding more power to a single central server, like upgrading its processor, memory, or storage. This approach is called vertical scaling. The MySQL setup was like this vertical system and primarily relied on a single main server, known as the master. Anytime information needed to be updated or saved or written. Having one server manage all of this is like having one air traffic controller manage an entire airport. Things are going to go very wrong, very fast. And Google knew this, and it was a matter of time before the entire system caved in on itself. So Google got to work. At first, it managed the load by dividing this giant database into smaller, more manageable pieces. Kind of like if you took an essay and pasted a paragraph on a separate Word doc instead of having it all on one. But as Google's databases became more and more massive, this sharding technique became less and less effective as even the little pieces were way too big to handle. So Google was forced to ditch this old way of handling all its data and began investing millions and millions of dollars into building something that would hopefully solve all their problems. Next one is Bigtable. Bigtable was Google's fancy new invention that let it ease the load off its database systems, and it made it solely for the purpose of scaling. But instead of vertically scaling, Google decided to scale horizontally. Bigtable worked by introducing a map that stored data across rows and columns. Each row had a unique identifier, and columns could be added as needed without a predefined structure, making it more adaptable than what MySQL was dealing with. It would then automatically split the data into the default unit called a tablet, which is then assigned to tablet servers that could be tacked onto the system without any performance loss. In plain English, Google had decided that it was better to scale by just adding more servers instead of powering up a single big one, and with some very fancy techniques that are way beyond the scope of this video, made it almost lossless performance-wise. The system also helped ease the issue of constantly updating data by tagging it with timestamps, which tracked how data changed, similar to version updates to games, and also made it a lot easier for the computer to manage data that had a lot of empty fields, called sparse data, which web indexing has to deal with all the time. The only problem here was that a big database like this is actually pretty useless, because what's the use of a database if you can't get people the information they want? Next is getting one data. As it was coming up with new ways to store data efficiently, Google also came up with the Google File System, or GFS, which got people the information they wanted quickly. It consisted of three parts: a master server, which keeps track of where everything is and coordinates queries; chunk servers, which store data in 64 megabyte pieces called chunks; and clients, which are you and me, the people who use the system. By breaking data into chunks and spreading them across many chunk servers, GFS could handle tons of queries at the same time, while also failing proofing itself against a server failure, since if one server ever failed, the other servers still have the same data and could still run with it. it. GFS also introduced a simple way of writing new data. Instead of constantly updating and changing old data, it just tacks new data on instead in an append-only style, which keeps it more accurate and free from errors. The system worked for a while, and GFS successfully handled huge amounts of data, from search to Gmail to Google Maps and everything in between. But if you were paying attention, you might have thought, hey, the master server configuration in MySQL was a bottleneck. Wouldn't the master server here in GFS also be one? And you'd be absolutely right. So Google was forced back to the drawing board again to avert a crisis that was coming straight for their door. Speaking of, thanks so much for all the support on the really means a lot, and I want to give something back to you guys. So, do you need a job? That sounded a bit weird, but whether you're a UX designer, app developer, freelancer, digital marketer, hacker, or just a curious viewer, I want to get to know you guys, share your field, and I have special gifts for you. Also, I made a Telegram channel for us and want to make this the place to be for professionals like you. I pinned the link in the comments section. Back to the video. When Google realized the oopsie daisy they just made, they decided to develop something to replace GFS called Colossus. Colossus, like Bigtable, removed the central master server by spreading out the control over many servers. But that's where the similarities end. One of the biggest improvement points for Colossus was something called data storage erasure coding. Instead of making multiple copies of data which took up tons of space, erasure coding broke data into smaller pieces with extra backup pieces called parity pieces that would help recreate the original data if some pieces are lost. This method was so effective it cut Google's storage costs in half, which, when you're talking about billions of gigabytes of data, is a really big deal. Colossus also introduced smaller chunks than GFS 64 megabyte size, which let it handle smaller files more efficiently. Imagine if you had a chunk that only needed to handle 1 megabyte in the past. GFS would allocate the entire 64 megabyte chunk to that, which destroyed efficiency with smaller chunks. Colossus could lose and could manage much more quickly, which was becoming a necessity as real-time applications started springing up everywhere as people got onto the internet. And actually, you're experiencing Colossus hard at work right now, since this is the very thing that helps YouTube and Google Ads function, where data needs to load instantly, or else you'd get an ad that takes 10 seconds to even show up, which would probably piss you off. The only issue with all these fancy technologies, though, is that it didn't address one simple question. How do we get this data out to the entire world? Next is getting the data everywhere. After Google solved the challenge of local data storage, they faced a new one: international data storage. Enter another one of Google's inventions called Spanner. The key to Spanner's success is a unique system called the TrueTime API, which uses atomic clocks and GPS technology to keep time perfectly synchronized across Google's global network. This synchronized clock lets Spanner track when data changes with literally atomic accuracy, allowing it to keep data in order even when it's stored in multiple locations, in order to make sure this data is the same everywhere. Google put into Spanner design something called the Paxos consensus, a method where servers essentially vote on whether or not a specific piece of data needs to change or not. It's like that veto sequence in Neon Genesis, where they were trying to get the computer to not self-destruct. It might not sound like a big deal, but when it comes to banking, finance, or even things like news or current event updates, having different things and different numbers in different countries at different times would be confusing and probably illegal. On top of all that, the Spanner is built to never slow down as daytime comes to one half of the Earth. The load on that half of Google's systems logically increases, so the Spanner was built to be able to shift data where it's needed most, automatically keeping everything balanced and efficient. Now the real challenge began. Latency. Latency is essentially lag, and having everyone outside the US encounter giant lag spikes when they're trying to search something up is not acceptable. So to deal with this, Google set up a system called caching and a content delivery network, or CDN. This is probably the easiest part of this big, complicated system to understand, because the CDN is literally just storing information that people probably want to see physically nearer to them than others. You wouldn't keep data related to the EU in servers in Indonesia, would you? So to make this more efficient, Google made what's known as the Google Global Cache program. Google partners with internet service providers or ISPs to store popular content directly within their networks, bringing it even closer to users, way closer than servers could ever be. This setup works incredibly well. About 90% of requests for popular content are served from a nearby cache, rather than Google's main data centers. This means less strain on Google's central systems, faster load times, and less angry people. Wins all around. In simple terms, Google's caching system helps them deliver data faster and more efficiently to people around the world. It's why millions can watch the same viral video on YouTube without any buffering. So now you know the gist of how Google gets data to you. What you don't know is how Google manages to keep the power on for all of this. Next, we have power efficiency. Google's data center is capable of handling billions of searches daily, consuming less energy per unit of computing power than a typical laptop. How Google designs custom servers optimized for efficiency, stripping away unnecessary components, and fine-tuning every aspect for maximum performance per watt. The real innovation, however, lies in their cooling systems. Some of the data centers use complicated water-based cooling systems, airflow schematics, and other fancy stuff. But the most common way Google does this is to literally just put servers in a colder place. Combine this with a ton of renewable energy investment and some smart engineering, and Google's power efficiency is almost as efficient as the light bulb you use in your house at a power usage effectiveness rating close to 1.1. This, combined with all the decentralization that Google has done, makes it so that the system runs crazy fast all the time and is crazy efficient. The only thing left to do is prevent this giant thing from failing. Google knows its infrastructure will fail at one point or another. It's just a part of life. So instead of waiting for it to happen, the system is constantly preparing for an event that hasn't even happened yet. There's the simple things like how Google uses load balancing to send traffic elsewhere in case one specific server goes down, and automated systems that check in on the system's health periodically so it knows when failure is imminent. But the most important thing here is the mindset that Google takes through chaos engineering. This practice involves deliberately introducing failures into the system to test its resilience. Engineers are literally paid to simulate a countless amount of failure scenarios to make sure the system knows exactly what to do when something goes wrong. Almost like ethical hackers, these combined strategies have enabled Google to achieve an uptime of 99.999% of an entire year. That means 25 billion gigabytes of data only ever potentially goes down 5 minutes in an entire year. No matter what your thoughts on Google are, its CEO, or the lawsuits it's facing, you've got to admit that is pretty goddamn impressive. So next time you type something into Google and hit the search button, realize that you're using what is quite literally the closest thing to an engineering miracle that humanity will ever see. All of this because two guys wanted to have a fun time with a quirky little research project prompt some 30 years ago.